Hey guys, in this next video we are going to discuss empirical and molecular formulas. In order to do that, we'll introduce the idea of a percent composition for a given compound, and then we'll review how to calculate the empirical formula and later the molecular formula from the percent composition. So the idea of this section is to discuss how chemical formulas are determined. And the way you do that is you use experimental techniques called elemental analysis, which are capable of analyzing the relative amounts and types of elements that are present in a given compound. Oftentimes, the results of an elemental analysis is the so-called percent composition, which gives you the percentage by mass of each element within a compound. The equation right here just reviews very quickly the definition of a percentage. So the percentage of a given element within a compound is the mass of that element divided by the mass of the compound times 100. Okay? And if you know the percent composition for a given compound, that is, if you know of the percentage of each of the elements within the compound, you can actually use that information to deduce different types of chemical formulas. And so that's what we'll go through in this section. Here we're going to start off by calculating the percent composition given the chemical formula. So we're considering the substance formaldehyde. We have CH2O, and what we want to be able to do here is to calculate the percentage of carbon, the percentage of hydrogen, and the percentage of oxygen in formaldehyde. And so we will need the molar mass of formaldehyde. That's going to be 12.01 for carbon, plus 2 times the atomic mass for hydrogen, plus, since there's one oxygen, the atomic mass of oxygen. So I'll go ahead and get that number very quickly. So I'm getting 18.02 for the, that's not right, is it? No, that's not right. There we go. 30.03. Grams per mole. Okay. And so what we'll do to get the percentage of carbon is we'll take this term here, the mass of carbon, 12.01, and divide that by the 30.03 and multiply that by 100. For the percent hydrogen, we'll take this term here, so 2 times 1.008 divided by the total, 30.03, multiply that by 100, and then we'll do the same thing for the oxygen. It's going to be 16 divided by 30 times 100. So I'm getting 39.99% carbon. 6.71% hydrogen, and I'm getting 53.28% for the oxygen. So these are the percentages, and if we add these up, they should add up to 100. Or at least within sig figs. Yeah, so I'm getting 99.98%. So within our sig figs, we're at 100%. So this is how you calculate the percent composition of a compound from its chemical formula. You basically use the molar mass formula to figure out what the parts are, and then you divide each part by the whole and multiply by 100. The next problem is identical to that, and so you would do the exact same thing, only you would need to use the molar mass formula for the ammonium nitrate. I'm going to go ahead and let you take care of that problem as an exercise. Here in this problem, we're taking the percentage of the percentages for formaldehyde, and then we're using them in a problem. So given the mass percentages that we've calculated, suppose that you had 83.5 grams of formaldehyde. How many grams of formaldehyde would that be? Well, you take the 83.5 grams of the total, and then to get the percent carbon, you would multiply that by the percentage of carbon divided by 100. And so that gives us 33.39 grams of carbon. And we might round that to 33.4 grams to be consistent with our sig figs in the 83.5. This problem is identical to the last one, only it goes along with the ammonium nitrate. So if you use these percentages, you then take the percentage of nitrogen, multiply it by the total amount of compound that you have, and then divide that by 100. Well, the next slide here goes back to this idea of an empirical formula. We talked about it briefly in one of the previous videos. Here I'm stating the definition again. The empirical formula is a formula that's derived from the elemental analysis of a compound, and it has the smallest ratio of elements in that compound, whether it's a molecular compound or an ionic compound. Contrast that with the molecular formula, which is the chemical formula for the molecule itself, or the chemical formula for the formula unit if you're dealing with an ionic compound. The term empirical, if you haven't heard it before, it means derived from experiment. So you perform an elemental analysis experiment, you use that percent composition you get from the elemental analysis to derive the empirical formula. And so here's some examples of illustrating the difference between the molecular formula of a compound and the empirical formula. So the substance hydrogen peroxide, it's a molecule. Each molecule contains 2 hydrogens and 2 oxygens. So the molecular formula is H2O2. The empirical formula, the one that you get from elemental analysis, is the lowest whole number ratio of the corresponding molecular formula. So you can reduce a 2-to-2 ratio down to a 1-to-1 ratio. So this is the formula that you would get from your elemental analysis. The compound acetylene is similar. It's C2H2. The formula you would get from an elemental analysis of acetylene would be just CH. Another substance, benzene, I think, which we looked at in a previous video, it's that ring-shaped molecule, that 6-membered ring. Each benzene molecule contains 6 carbons and 6 hydrogens, and you can reduce that 6-to-6 ratio down to 1-to-1. So you'll notice that 2 different molecules with very different properties. They have very different molecular formulas, however they have the same empirical formula. Okay, so elemental analysis can only show you so much. Okay, it only gives you the lowest whole number ratio of the elements within a compound. Here's an ionic compound, sodium oxalate. We've also looked at this guy in a previous video. This is the actual formula unit for sodium oxalate. The empirical formula, however, is going to give you only the lowest whole number ratio. So you can reduce a 2 to 2 to 4 ratio down to 1 to 1 to 2. And so this is what the elemental analysis is going to give you. So the empirical formula, generally speaking, has less information in it than the molecular formula or the formula unit for a compound. The two formulas are related, right? If you take the subscripts in the molecular formula and divide by a factor of 2, that gives you the subscripts in the empirical formula. That's true for all of these. And so you can relate the mass of the molecular formula via this integer to the mass of the elemental formula. And so if you are able to perform an experiment where you can measure both the mass of the element of the empirical formula and the mass of the molecular formula, you can use that to calculate what this factor n should be. And that provides you with a way of deriving the molecular formula from the empirical formula. And so we'll see a problem like that later on in this presentation. So what are we being asked to do here? Let's see, we've got a compound of nitrogen and oxygen, and we know how much it weighs. So we know the mass of our sample. And an elemental analysis shows that it has 0.483 grams of nitrogen and 1.104 grams of oxygen. We're being asked to determine the empirical formula for this substance. So the way I like to set these up is I want to write down, I know that the empirical formula is going to have the generic form NX OY. And my goal is to determine what these subscripts X and Y are. And so what I'm going to illustrate is the procedure for doing that. What you want to do is to calculate the number of moles of each element. Okay, so to determine X, what we're going to do is we're going to take the number of grams of nitrogen and we're going to convert that to moles of nitrogen. And we do that by dividing by the atomic mass of nitrogen, which is 14.01 grams. So we're going to get that number. We're going to do the same thing for the oxygen. We'll take the 1.104 grams of oxygen and we will divide by the atomic mass of oxygen. And that's going to give us moles of oxygen. So I'm going to get those numbers real quick. 0.034, we'll call it 5. And for this one here, 0.069. Now, obviously, we're not used to having decimal numbers in our chemical formulas. In fact, that's not desirable. What we want to do is to get these into whole numbers. And so what you want to do is take a look at the two numbers, and then you want to divide by the smaller of the two. So I'm going to take the 0.0345 and divide both numbers by that number. That's going to give you 1, and we're going to find that that is going to give us 2. Okay? So the empirical formula for the substance is NO2. Okay? So you take the grams that you're given, convert that to moles, and then look at the numbers and divide by the smaller number of moles. And that's going to give you oftentimes whole numbers, which is what we want. Let's do another one like this. Let's see. I think we want to do we should do this problem instead. So this problem here is essentially identical to the one that we have looked at previously. So what we will do is we'll work this problem here. Here we've got sodium dichromate, and we're given the percent composition of sodium dichromate. So we know that the percentage of sodium is 17.5. We know that the percentage of chromium is 39.7, and the percentage of oxygen is 42.8, and we are being asked to find the empirical formula for that compound. So we need to figure out what the X, the Y, and the Z are in this generic chemical formula. So what we'll do is we'll just assume that we have 100 grams of compound. By assuming that we have 100 grams of this compound, then we can then just write these numbers here. These will be just the masses of the elements that we have. So if you have 100 grams of compound, you're going to have 17.5 grams of sodium, 39.7 grams of chromium, and 42.8 grams of oxygen. So we'll make that assumption, and then we'll do what we did before. We'll calculate the number of moles of sodium. Okay, I believe it's 23. I'm going to pull up my periodic table just so I don't mess this up. So for sodium, we'll just, all right, 22.99. 22.99. For the chromium, we'll take that 39.7. We'll multiply it, we'll divide it by the molar mass of chromium, which is 52. And then we will do for oxygen, we'll take the 42.8 grams, and we will divide it by its molar mass. Like that. Okay, so I'm going to calculate these numbers real quick. So that's what I'm getting for the sodium. That's for the chromium. And here's what I'm getting for the oxygen. So what you'll want to do is to take a look at these moles and figure out which one is the smallest, and then you'll divide all three of them by the smallest number. So that's the 0.761. Okay, that's going to give you 1. This is going to give you something that's very close to 1. And then for the other one, we're going to get approximately 3.5. Not quite an integer, is it? No, it's in between two integers. And so we can write that as 3 plus 1/2, like so. And then we can convert that to a ratio like that. So now what we want to do, we want to get rid of that fraction. We'll multiply all of these numbers by the denominator here of 2, so that we get the empirical formula is that, where this is this, the subscript for oxygen is the number 7. Okay, and so that's the empirical formula for this compound. This problem is very similar. So benzoic acid contains carbon, hydrogen, and oxygen. So you'll want to set up the generic empirical formula. You'll assume that you have 100 grams of compound, and then you'll take each of these percentages, you'll just take that to be the mass of carbon, hydrogen, and oxygen, respectively. You'll then calculate the moles of each, and then you'll divide each of the moles by the smallest number of moles, and then you'll use that to find out what the subscripts are in the empirical formula. You may need to make an adjustment at the end to get rid of any fractions that you have. Okay, so this is a different type of problem. So we'll go ahead and work this one out. In this type of problem, we are combining the empirical formula with the second experiment, an experiment based on mass spectrometry. We've talked about that previously in the context of isotopes, but there's a separate experiment that you can do to measure the molar mass or the molecular mass of a given compound. And so if you know the molecular mass and you know the percent composition in the empirical formula, then you can determine the molecular formula of the compound. So let me illustrate what we're doing here. So the empirical formula for the compound in this problem will be CXHYOZ, something like that. And the molecular formula is going to be similar to that, except there will be some integer n that we multiply all of these subscripts by to give us the molecular formula. So our goal is to basically calculate n, x, ny, and nz, and that will be the molecular formula. Since all we know here is the percent composition, we'll do the same trick that we did before. We'll assume 100 grams of compound, and then we can take the mass of carbon to be 39.9, the mass of hydrogen to be 6.7, and the mass of oxygen to be 53.4. And so we'll use those masses and convert them to moles. So we'll take the 39.9 grams of carbon and we'll divide by the molar mass of carbon. We'll do the same thing for the hydrogen. And likewise for the oxygen. Okay, so I'll do these calculations real quick. We'll take a look at each of these number of moles and we'll divide by the number of moles that's the smallest. So we'll divide by 3.32, 3.32, 3.32. This is going to give us 1. This is approximately 1. This is going to be equal to 2. Okay, so we've just found that the empirical formula is CH2O. Now what we need to find is the molecular formula, which is going to look like this. We need to find the value of n that takes us from the empirical formula to the molecular formula. Here's how you do that. First, you need to calculate the mass of the empirical formula. Okay, and so using this formula, it's 12.01 plus 2 times 1.008 plus 16. We get 30.026 AMUs. I could have used grams per mole, doesn't really matter. Now, to get the value of n, what you want to do is to take the molar mass of the molecular formula, which is given to us in the problem. It's the 60 AMUs, and you want to divide that by the molar mass of the empirical formula. So we've got the 60.0 up top divided by the 30.0 in the denominator, and that's going to give us a value of 2. And so that tells us that the molecular formula is C2H4O2. Okay, so this is the new step. Like we did all of this in the previous problem, but then the new part is determining the value of N that takes you from the empirical formula to the molecular formula. And you need an extra piece of information. You need the molar mass of the compound, which is determined in a separate experiment. Well, this problem is identical to the one that we've just worked, so I am going to leave this as an exercise for you to try. Here we just have some conceptual questions. I think this would be a good problem to look at. So let's go ahead and work through this. Okay, so you have a friend that has some questions about empirical and molecular formulas, and you can assume that they are good at performing calculations. So he's worked a problem to determine the empirical formula for a compound, and he came up with the answer C2H8O2. And the question is this a possible answer for an empirical formula? And you have to think about what an empirical formula is. The empirical formula is always the lowest whole number ratio of elements within a given compound. And here you can see by the subscripts that he's found 2H2 is not the lowest ratio, right? The lowest ratio would be C4O. It would be CH4O. And so this isn't possible to be an empirical formula. And so he needs to go back and look at his calculations and make sure that he's got the lowest whole number ratio in the subscripts. For a different problem, he's come up with C1.5H4 as the empirical formula. And this is not what we want either, right? We don't want to have fractions as our subscripts in the empirical formula, typically. And so what he needs to do is he needs to multiply these two subscripts by 2 in order to get rid of that 1/2. And so once he does that, he'll have C3H8 as the empirical formula. And that would be the proper form for an empirical formula. One more question. He completed a problem of the same type as above, and his answers indicate that the compound had an empirical formula of C3H8O and a molecular formula of C3H8O. Is this result possible? It actually is. The integer relating the empirical formula to the molecular formula could be the number 1. And so this is also a possibility. It can be that the empirical formula is identical to the molecular formula. Well, that's going to do it for this video. So I'm going to go ahead and stop it, and we'll talk about molarity in the next one.